Thank you very much, John. All right, good morning. It's pretty exciting because we have a Datalog session. So I've been doing work on Datalog from the PL side for like 10 years now, but I don't think we ever had a Datalog session at one of the major SIGPlan conferences. So that's pretty cool. So Datalog. Datalog is a rule-based language. You have rules like this. This is the typical example many of you may have seen, but I'm going to repeat it for those who are new to Datalog. So we have a path, and you have a path from A to B if there's an edge from A to B. And you have a path from A to B if there's an edge from A to C, but also a path from C to B. So that computes the transitive closure of the edge relation. Okay? And so then you take some data, which here would represent the edges, and you compute some relations, which here would represent the transitive paths. All right, so Datalog comes from the database community originally, and they dealt with small queries running against large amounts of data. Okay? But now we're doing Datalog at PL, right? And we have a lot to contribute, but there's a slightly different setup. So the queries that we consider here in PL, they're typically much larger, and the data is relatively small compared to what's used in the database community. And so one of the examples of things that we do in the PL community is write program analyses in Datalog. And so here's a small extract of points to analysis for Java, which is part of the dupe analysis platform. And actually, this is really a small excerpt. So here's a graph that shows nodes. Each node is a relation defined in the Datalog program, and the edges are their interdependencies. Right? So this is a Datalog program with hundreds of relations. They all have complex dependencies on one another, and it's really difficult. And these are the kind of programs we deal with in PL. Okay, so what are the PL research questions about Datalog? Well, from what I can see, it's mostly these three. It's performance, expressiveness, and programmability. And because we care about these aspects of Datalog, a growing number of Datalog dialects have been proposed in literature. So here's some of them. You may have heard of Soufflé. It's one of the most well-known ones in PL. Inca is one that we are developing. Then there's some older ones like BDD, BDDB, Datalog, Aglog, Formlog. We will hear more about Formlog today, QL, and so on. And so traditionally, all of these Datalog dialects also come with an engine, right? And so you have different Datalog engines, and there's like a one-to-one mapping between the dialect to the engines. Okay, so that's not so great. And what's the problem here? Well, the first problem is interoperability is lacking. So if we have no source interop, that means if I write a program in Soufflé, I can't use it with the solver of Inca. Right? We also don't have binary compatibility. If I have two programs, one written in Inca, one written in Soufflé, I cannot link them together. I can't use them together. Okay? And if Soufflé implements an optimization, the other Datalog engines either have to re-implement it or not have it. And so one of the solutions we know from compiler frameworks is we can design an intermediate representation, the Datalog IR. And then all of the dialects first translate to the IR, and then we translate the IR to all the backends. Okay? But here comes problem two. The second problem is that the Datalog dialects all define custom extensions to Datalog as you know it from textbooks. So for example, Soufflé has algebraic data types. Inca and Formlog have functions. Datalog has state. These are all things that don't exist in textbook Datalog, and what you would also not in the Datalog dialects you see in the database community. Okay, so we need a more sophisticated design. And so let's zoom out a bit. And instead of having one Datalog IR, we're going to design, or we have designed, a core Datalog. And that's really like textbook Datalog, which is extensible. So you can write lots of extensions to this IR. Okay, and then something like Soufflé, the Soufflé compiler front-end actually uses a whole bunch of these extensions like booleans, numbers, algebraic data type aggregation, disjunctions, and so on, right? And it can generate not just core Datalog, but also using these IR extensions. But we still have a problem. The problem is the ascent solver, which is one Datalog solver written in Rust. The ascent solver now seems to have to implement all of these extensions. right? And that's not so great either. So what we do is we actually design a multi-level IR where you have lowering steps. Lowerings are like the sugar rings, but between IR extensions or towards the core IR. And that means that in the compiler backends, you only have to implement those things that cannot be lowered. Okay, and then we add one more thing. So in this paper, and this is also the focus of the remainder of the talk, we add static typing. And we want static typing in a way that you can define extensions. And these extensions can very precisely declare their static semantics to make sure that, well, two things. So first, optimizations can assume you have valid code to begin with. And secondly, there's a lot of code generation going on now. We have the lower rings, we have the compiler front ends targeting the IR. And we know code generation is really difficult, and type systems help with figuring out when something goes wrong. Okay, so what we end up with, and that's also the title of this talk, is a typed multi-level Datalog IR. Okay? And so in the remainder of the talk, mostly I'm going to talk about the type system and its design, which I think is pretty interesting. So let's look at what kind of type system we need for Datalog. So, and we're going to start with core Datalog. Well-typed core Datalog programs are not supposed to go wrong. So what can go wrong? Well, first we have what you expect. We have kind of type compatibility issues. So for example, if I'm trying to add a string and a number, that shouldn't be allowed because they don't have compatible types. Or if I'm declaring that the column X of relation city has type string, but then I'm assigning the number 3 to it, to a logic variable that will feed into that column, that shouldn't be allowed. So we can have incompatible types. There's nothing particularly interesting about this aspect of the type system. And so what's interesting instead is reasoning about variables. Because we have logic variables in Datalog, and we want extensions to be flexible in the way that they can introduce bindings and binders, and we will see more of this. So what are the kind of problems? So this rule is invalid. It's invalid because we're using X as an operand to multiplication, but operands cannot bind variables. So at this point, X is unbound. So in Datalog, you're trying to compute the X's that satisfy the constraints on the right-hand side, right? And so this rule cannot be solved by a Datalog solver because we don't know what X's to put into the column. Right? And the problem here specifically is you cannot bind variables when they are in an operand position. Here's another example. This relation has two output parameters, A and B, but we're only binding B. And this is a property known as range restrictedness in the Datalog literature. And that's an example where the variable has to be bound, but it is not. Here's another example. This is a Datalog relation, again, two output parameters, and the body is an equation constraint. And equations are kind of good because they do bind variables. If you do, like in our city example at the top, right, we have x equals 3, and that binds x to 3. But if you do a equals b, and neither of them is bound yet, then this constraint cannot be solved. And then finally, one more example, if you have negative calls are like checking that something is not in a relation. And since the complement of a relation is not necessarily computable, you actually need to know what you're checking for. So you need to know what A and B are before you can check if they're not in path. And again, in this example, A and B are unbound. So how can we reason about the boundedness of variables in Datalog in a way that it's precise and extensible by extensions? Okay, so let's look at this rule again that we saw at the very beginning of the talk. It's the transitive closure path rule. So we're going to distinguish the status of variables, and we're going to mark them, decorate them in the program. So the open circle says it's a binding occurrence. So this is the place where x gets its value, whereas the bullet is a bound occurrence. This is where you're reading the variable. And now we can annotate the rule with this notation. And so what we get is, in the first atom, edge AC, we're actually binding AC to the tuples that are in the edge relation. And then the second atom, we're reading C, it's already bound, and we're using it to bind B. And so this binding information actually shows us kind of what the underlying index structure is going to be of these relations, which is also nice. And then in the end, we can check that A and B in the head of the rule actually must be bound. These must be bound occurrences, right? Otherwise, we're violating the range restrictedness. And so here's the second example, kind of the same rule, but a little bit refactored. A and C are again bound in the edge atom. Then we have an equation. That equation acts as an assignment. You're assigning C to D, and that's because C was already bound and D was not. And then you can use those again to query path, and A and B are bound in the end. So kind of this is an observation of how this information of boundedness flows through a rule. And by the way, we're forcing evaluation order here, which is left to right. So we can take this now and start designing the type system. So here's the typing context. A variable can be unknown, or it can have one of two statuses. It can be declared, which means that we know its type, but we know it's not yet bound. Or it can be bound, which means we know its type, and we know that we can read from it. OK, and so if we take this context, then we can start designing a type system. So here's the first approach, the first try. We designed a bidirectional type system, which is flow sensitive. It needs to be flow sensitive because the binding of variables kind of happens on the fly during the rule. And then we get these kind of judgments. They're pretty standard. Term checking is like expression checking in other languages. You have a context and a term, and checking means you are given the type, and you compute the resulting context. And term inference is the same, but you're also computing the type on the fly. And then there's atom checking. And so I'll just show you two example rules. So here's one rule that says, if you want to check a variable and you are given the type of that variable, then after that variable occurred, it's bound and has type T. And then here's another one. This is for equations. For equations, there are two rules. I'm only showing one. You need to infer the type on one side of the constraint, or on one side of the equation, here for T. And then you can use that type to check on the other side of the equation, here, U. OK? So that looks kind of promising. And indeed, for the examples I showed before, this works out fine. So you can use these rules to actually show that A and B will be bound at the end of this rule. But they don't work for the kind of the counter examples I showed. So let's go back to the square root 4 rule, where we had x as operands. The typing rules we've designed so far cannot distinguish whether we are in a position where binding is allowed or not. And that's why what it will do is when x occurs as an operand first, we will just bind it. So that becomes a binding occurrence. And then the second operand is reading. And that doesn't make any sense whatsoever. So there's clearly something wrong here. And so there's one thing we need to add. And that's kind of what I think is the most interesting novel design aspect of this type system. And we need to make it bipolar. So bipolar is basically just a Boolean flag. And so the judgments now have this polarity, which is either positive or negative. And what it means is this. If the judgment is done with the positive polarity, we are lenient. We allow bindings to occur. But if we have a negative polarity, then we are strict. We don't allow any new bindings to occur here. Okay, and so here's an example. So let's do the multiplication rule. That was the problematic case in the square root rule. And the multiplication rule now can be explicit about whether it allows bindings to occur in the operands or not. Right? And what we do here is we say, OK, we can check T and U. We know the type that we expect. And the polarity is negative, which means no bindings allowed. Right? And we can do something similar for equations. Right? We had this problem where on both sides of the equation was an unbound variable. We can disallow this by requiring that we need to have one side needs to be checkable in a negative polarity, so without doing new bindings. And then the other one can bind, so we can have assignments. And so this is pretty nice, and it's actually also extensible. So I'll just show you two extensions. So this is for nested disjunctions. Nested disjunctions, this kind of a standard technique for flow-sensitive type systems. So we do the meet of the two resulting contexts, which means Only those things bound in both alternatives are guaranteed to be bound. But one of the most interesting thing is actually negation. So what is the polarity of negation? The polarity of negation is really just the flipped one. So if you want to check if not A is valid, it's enough to check A, but you negate the polarity. And then you get this nice property of double negation elimination that we would expect, but now the static semantics actually explains also that that's what we do get. So what happens here is if you have two negations, you flip the polarity once, you flip it twice, and that means you're back to where you started. And so effectively we have eliminate the double negation in the static semantics. Okay, and this is really flexible. I don't have time to show you how flexible it is, but we've implemented the system and we've developed a lot of different extensions. I'll just mention a few highlights. So we have a lot of first-class data structures, records, lists, sets, and maps, and we can precisely describe their binding structure. We have demanded parameters, which is like giving the programmer a handle into the magic set transformation. You can say this parameter needs to be bound and the binding needs to come from the outside, and this is kind of really playing around with the binding structure. Parametric polymorphism, stateful variables, and all of these extensions, a lot of them actually need to use the polarities very smartly to have the static semantics be precise. And so what you get by using all of this is this type multi-level IR. And this is really cool because it allows us to do something that wasn't possible before. What we can do is we can take a single source program, translate to the IR, and then target one of different Datalog backends. And what we did in the paper, just to illustrate that it's possible, is take one dupe points to analysis and translate it to different engines. And we can actually now compare the performance that these systems have on the exactly same program. Because what you've done, what you see in the literature so far is that people have hand translated the Datalog programs to meet the different dialects constraints. So one question you may have is, how much effort is it actually to develop these compiler front ends? That's something we discussed in the paper. I just want to, show you the kind of the key result here. And because we have all these IR extensions which are reusable across front ends, writing the compiler front end itself becomes really easy. So for example, we have about 300 lines of code to compile Soufflé to our IR. We have about 250 lines of code to compile a fully functional programming language to Datalog, and an object-oriented language that David will talk about in the session later. That's a little bit more effort, but still very much manageable. And so for the functional programming language, we had a compiler before, and this gave us a 10-fold reduction in code size. So let's summarize. We developed a type system, which is bidirectional, flow sensitive, and bipolar. And we show that you can use that to precisely describe the static semantics of Datalog. And it's also extensible in a way that extensions can very precisely manage their own bindings and how they change bindings. And then we've implemented this in an open compiler framework that we've implemented in Scala, and we have developed or implemented 4 front ends for that framework so far in 3 backends, and a module system that we presented at Gypsy here at Splash as well. And now the next goal for us is actually look at IR optimizations that can apply and be useful across all these different backends. Thank you very much.
Hi, thanks for the talk. It seems like very interesting work. I was curious, when you were talking about the polarity, it reminds me a bit of the modes from some Prolog systems. Is there any connection, or am I just imagining that? Thanks.
Right, thanks for the question. So the modes in Prolog, they're on the parameters of the rules. And I would say that the polarities is a generalization of that. Okay. It's a generalization in the sense that you can have that at any place during the typing derivation. And not just at the parameter. So the not rule illustrates this a little bit, where in the middle of the Datalog rule, you can have not of something, and you're actually just negating this.
Okay. Yeah. Thank you.
Good question, thanks.
I'm more concerned. Hi, great talk. I'm more interested in some of the practical part of this. So like, what we're giving up by doing this IR, I guess. So if we have like Souffle front end going through your IR into the Souffle back end, how does that compare to Souffle out of the box? Both in like, you know, would you end up with the same problems being posed to the Souffle back end, or is it, you know, does the lowering do the lowering differently than like Souffle out of the box would today, if that makes any sense?
So if you have a Souffle source program and you basically pipe it through our framework, the resulting Souffle program would be almost identical to the original one. And that's because the compiler backends can choose which lowerings they need. So oftentimes when a compiler backend already supports some extensions, then we would leave it to that compiler backend to do the lowering internally.
I see.
Okay. Which is a choice, right? We don't do it for everything, but for some of these things.
That makes sense.
So that's a choice. And in general, now you can describe very complicated pipelines where you choose what to lower when. And in particular, the compiler backends don't need to support all the extensions either, right? Just the ones that cannot be lowered.
Makes sense. Thank you.
Yeah, thanks.
Okay, let's thank our speaker again.